Excellent. Yeah, these guys are really fast on the videos. So anyway, Don Smith virtually needs no introduction after this afternoon's presentation. It was excellent. He was our surprise speaker when somebody didn't show up and didn't tell us he wasn't showing up. So Don came through in fine style, and he's going to tell us a few finer points that he didn't have a chance to cover this afternoon. That's going to be part of what he does. And then he's also going to show us some hands-on demos tonight. Don has a background in geology. He's done some incredible work, and I think this is really neat because the insights into free energy can come from any discipline, literally. I've gotten insights from music. He's gotten them from geology. Of course, the EEs get insights, but anybody can help in this stuff right now. And Don has really done a fine job helping out. So let's welcome Don Smith for our workshop.
Here.
Huh?
Am I on go?
You're on go.
Okay. Thank you. We only got to page 3 on my speech this afternoon. So do you want to maybe finish up a little bit on that and then go into the other thing? Okay. Okay. If someone will hand me this little blue thing here, we'll see what we can do about it. Thank you very much. Okay, when you're writing a speech, you never really know how long it's going to take, and this one apparently took longer than I thought. Let's see, here we go. Okay, we didn't actually get to look at any of the devices as such on... Okay, is that working? Okay, you want to look at it for a couple of minutes here and then we'll start talking about it. There's a number of unnecessary parts there that were actually put in there because people expect to see them. Actually, on this, you can take everything back this way and take it off of there and it will work just fine. You can also take the spark gap off of it and it will still work just fine. And the reason for that is that in the coils, they have their own specific resonance due to the fact that they have both capacitance and inductance. And when you cross that on a chart, you find that that particular length of wire will have a specific frequency, and it will load and unload by itself, and you don't need spark gaps or you don't need anything else. Your Tesla coils can be built the very same way. This is a Tesla coil device. The Tesla coil in this case is in number 7. It's potted inside that laser module. And that laser module is about 3 inches long and about 1.5 inches wide there and about 1 inch deep. So that'll give you some idea of the size of them. I'm going to show you after a while when we get into the actual core part of this thing, some little modules that are about the size of a calling card, and they put out 1,000 volts. And they don't look at all like what you think a Tesla coil might look like, but they're still, that's exactly what they are. Okay? Anyone is okay to go ahead and move it? Okay, the one you're looking at there can have a very wide range of voltage. It can be up to 5 million depending on the parameters that you build into it. The one that you're actually seeing there is the one that was on the board this afternoon, which I showed you, the larger one. That's the device right there. Except that it's got fewer windings on this L2 thing, and it's also wound in a spiral way. Okay, we'll just sort of take this as it comes here and see what happens. We were talking about in resonant circuits that your impedance or your resistivity, or whatever you want to call it, which takes the place of ohms, becomes zero, and therefore you're at superconductor conditions at that point. The little statement over on this end where it says resonant energy explains it all, and we'll go into it in some detail in a little bit. Okay, basically what happens when the volts and amperes become equal, you're into what's called a volt VAR system, volts amperes reactive. And you can look in as many radio books as you want to, and you're not going to find hardly any of them that will give you an explanation of that. And if they do, it's misleading in almost all cases. But basically what it means is that your system resistivity becomes zero at resonance, which means that you're at superconductor conditions at that point, at room temperature. Excuse me. Okay, shall we do something else? Okay, in over unity devices, the statement at the top of this particular slide. Ma'am, push it farther up. Okay, I'm sorry. Is that better? Okay. A real fine example of over unity would be the fact that in induction, the rate of induction is directly related to the cycles per second. So if you want to establish a reference point there, at 60 cycles a second, square that, and then if you want to see the relative position of, say, 220 megacycles, square 220 megacycles, and compare the ratio between the two squares, and you've got the ratio of improvement with the higher frequency. So if you look at that from a standpoint of over unity production, you'll see that on this curve here that you've gone from a certain level of under unity type situation down here, which is what is normal to most things, and then all of a sudden whenever you get into the above 20,000 cycles per second and start climbing up between that and 200,000 cycles per second, the curve does this, just above 200,000 cycles per second, and it stays that way all the rest of the way. Okay? Well, we're talking about if you, like you made a chart and you showed the efficiency of the device, and the efficiency of the device as far as induction is concerned at 60 cycles per second is here, and the efficiency at 200 million cycles per second is up there somewhere. The ratio between those two is telling you your efficiency. Okay? And that's one of the reasons why I built this device, to get away from the ranges which the Tesla coils normally operate in, which is down below 200,000 cycles per second. And their Tesla coils are disruptive, and they have other habits which are not enduring. And if you get up into the radio frequency, you've got a device which is not harmful to humans, and you can handle it with millions of volts going through it, and you won't have anything happen except maybe the hair on your hand stand up a little bit. And you can also hold light bulbs and light them and that sort of thing. And the reason is that radio frequency, the electrons are running around on the outside, and they do not penetrate to any depth. And that's one of the reasons for the high efficiency rating. In the lower frequencies, the electrons are running through the wire, and they're bumping into things as they go, and they're not functioning very well. They're under unity. Once they get spinning outside the wire, then they're kind of free to do their own thing. and they don't have anything diminishing their effectiveness. Okay? Okay, did we talk about dominoes this afternoon?
Yeah.
We did, okay. Okay. And we talked about Ohm's law, and we also talked about how to recognize over unity. I'll put this back on and let you look at it a little bit more if you want. Let me step out of the way here. You can see where the envelope is set up and where the thing has passed outside the envelope there, and it continues even greater distance outside the envelope as it goes along, and it gets out to a certain point here, and it collapses, and then it comes back and starts the whole thing over again.
That radio?
This is a particular resonant circuit that you find depending on how you work your shunt on the resonant circuit. If the first one, there were three of them, if you remember. The one at the top is the one which you normally expect to see. That's where your dampening effect happens when you're seeing these things on the oscilloscope screen, and it's showing the analog, or whatever you want to call it, showing the cycling. And it starts out with a certain amount of energy, and that gradually diminishes. Okay, the second one there is another setting on that same resonant circuit, and with a slightly different adjustment, and it shows an envelope of energy very similar to FM carrier. And FM, you have a compression of these cycles, which takes the place of in the analog system, where you have various modulations on it. But and the third one is a particular arrangement of the grounding shunt, which means that its ability to communicate with the electron source, which would be your grounding, and the resistance there is like a dam on a large body of water, and it lets the electrons through, and they get caught behind this dam. This whole device is like a pump. All it's doing is, like the dominoes we were talking about, is tripping the electrons here, and that electron's tripping the next one, and this whole bunch of electrons in all directions are being tripped, and each time one of those would be tripped, it gives off a magnetic impulse first, and then when it comes back on that infinity loop, it gives off an electrical impulse. And this just goes on perpetually. The electron is never diminished in any way. It's giving you light and a lot of other things, and that is also an over-unity device if there ever was one. So if the physics books have a problem with that, so be it. Okay?
Mr. Smith, did you say you had a book that had, have you written a book that incorporates that information?
Yes.
You have written a book?
Yes.
It's in the bookstore?
Well, I'll show you what it looks like. I've got one right here.
Okay, is it in the bookstore?
They are getting some printed up just now.
Okay.
And they may have them before we're finished here. And they may not be quite as nice as this one, but these I did myself. And you remember they have nice colored photographs in them. And
Oh, that's great.
that sort of thing. So that was the actual device you were seeing this afternoon. One of them.
Okay, great.
Okay? Okay, let's see what else we have here. Okay, I'm going to take the speech, which I didn't get to make, and I'm not going to make the speech. I'm just going to check and see if some of these things I didn't talk about. Okay, whenever we get into how we get these magnetic flux measurements, we go back to years 1777 through 1855, and about the same time for another fellow. We're talking about C.F. Gauss and H.C. Oersted. And they were both trying to establish the electrical background field for the Earth with the external influences removed. So as it turns out, one of them did his measurements at night and came up with he came up with 50,000 volts, and the other one did his measurements during the day, and he came up with 100,000 volts, and that's per square meter of surface area. And this is above the ground with the ground influence removed, and it's the normal natural electrical charge that's in the air at that point. Now this varies depending on the time of day, the sun, influence of the sun, and sunspots, and a lot of other things. And sometimes, instead of being those units which I just gave you, it goes up into 2.5 to maybe 5 million volts per square meter of plate surface. And this does not take into consideration the other measurements which I was telling you about from the colored maps. The influence there is strictly from the character of the minerals and the ground and that sort of thing. So there is a huge amount of energy out there, and you need a device which can pump it or move it from one spot to the other and make these voltage differences so that you have a potential. If you have the same voltage here and the same voltage here, you don't have any potential difference, so nothing's going to happen. Yes, sir?
In the schematic that you showed of the coil, or approximately of the device that you had on,
Yes.
It showed a capacitor connected to ground.
Yes. Okay, that is a blocking device. It could either be a resistor or a capacitor or a variable of either one of them.
Is that grounding device the source of the negative impedance?
Well, see, you've got two coil systems there that are working, so you have to tune one of them to make, you have to have one of the coils with a tunable device on it, so the grounding, you can stick it in the grounding end of it, or you can put it somewhere else, but it's convenient to put it into the ground.
Well, you mentioned that the source of electrons for the system
Would be coming from the Earth.
Right. Is that the source of the effect that you get in your system?
Yes.
To show a negative?
If the electrons are not coming out of the ground, they're coming from either an air grounding or an earth grounding.
But there's no other device that you require on your coil?
No, it's very simple. As a matter of fact, when I started building these things, I put all kinds of things in there that everyone thought should be there, and which the books on coil building and Tesla coils and everything said, well, we need a spark gap, we need this, and so on and so on. And when I realized that a wire has its own induction and capacitance and that sort of thing, well, that told me immediately that I did not need a spark gap, because it's going to load and unload based on the frequency that's attributable to that piece of wire.
Do you need to put it in a...
The spark gap is not a necessity.
Do you need to put it in a particular geological area?
It started out that way because of these high concentrations of negative electricity in certain areas. And the problem in the very beginning was how do you get, you've got these two areas of different potential. So how do you turn that into something useful? And it became obvious that you were not going to be able to put a cable between the two, because a cable of any size, regardless of how large, was going to vaporize like a flash bulb whenever you grounded it. So with that in mind, it became obvious that there's more than abundant electrons everywhere, so you really don't have to be concerned about the fact that you're in an area of higher concentration, except that your devices will work a lot better. For example, where I showed you the 16 trillion deal, if you put a radio station in an area like that and ground it, they will hear you throughout the universe and several other universes. And that may be why NORAD's over here in Cheyenne Mountain. Okay? This most likely reason that they can have a command thing there that they can talk to anywhere in this world and any other world you might want to think about, with the potential that they've got in that rock mass over there. Okay? Okay, we're talking about Carl Gauss and Oersted. Well, we're getting units of flux, magnetic flux, bear their names, and we have to relate those to other units of magnetic flux in order to see how this thing all ties together. These maps that you were looking at were made in gammas. They sometimes are in nanoteslas and sometimes other units, but the most common is, say, gamma. Nanotesla and a gamma are equal in rank. A gamma would be equivalent to 10 active volts of electricity, or 10 volt amperes of electricity, if you want to put it that way. Okay, when you get into the other units, Gauss, of course, is 100,000 volts. It's a unit of measure of flux density. And Oersted is 50,000 volts. Now, 1 Tesla is equal to 10,000 Gauss. So would somebody real quick like to tell me how many volts 1 Tesla is? It's a bunch of them, isn't it? A big bunch. Is it 10 million or 10 what? A Tesla is how many volts equivalent? I think it's probably 10 million. So it's a rather large unit, and in practical terms, I'm not quite sure what you can do with a unit that large. Okay? Of course, the entire Earth has been surveyed due to the desire for atomic minerals and Cold War-related things. And these background maps on the magnetic flux were used for reconnaissance surveying, for zeroing in on areas which had promise as far as certain types of minerals were concerned. Now, where I come in, they are also used for locating oil deposits. It's a real fine tool for locating very large oil fields without drilling for them. There's certain characteristics you look for. Okay, let's see.
Can you purchase those? Who prints
Those maps, the United States Geological Survey in Denver has catalogs, and you can get maps on any square inch of the earth that you want to put your finger on. And there's several other groups that do them. And also the Russians do them, and a lot of other world governments for various reasons. Originally they were mostly done for military reasons or for some kind of strategic mineral that was required. Okay, whenever we get into energy and mass and that sort of thing, it becomes obvious that we have basically about 3 different situations that we can describe. We have a steady state energy, which would be static or pre-energy, and it's where mass attracts mass and where gravity dominates. Okay, in the unsteady state, we have two different types of energy derived from mass. We have kinetic energy, and we have we have 2 kinds of kinetic energy. We have expanding magnetic energy, and it's dominant for that, and it gives you your electrons moving apart, pressure decreasing. It gives a cooling effect. That explains why it's 276 degrees minus out in open space away from the Earth. And when the electrons are moving apart or expanding, it's cooling, and sometimes very cooling. Okay? There's less scattering of energy in an expanding situation. Okay? In addition to that, you have negative resistance as dominant. Okay, we go into the contraction stage of energy or mass. We get electrons moving together. Pressure is increasing. Heating effect dominates, and you have a scattering of energy, and positive resistance results. Okay, your under unity people work primarily in that particular set of circumstances. Most of the things that the under unity organization involves themselves in relates in contraction of electrical energy or dissipation of it or that sort of thing. Okay? Functions of active electrons. Electrons provide us with a lot of things other than electricity. And among those we get magnetic effects, which are useful in causing motors to turn. The magnetic thrust there is against gravity, which gives the motor the kick to start it turning and keep it going. Okay, that's the gravitational thrust as in electric motors. Okay, electrons are a source of visible light. When two electrons get too close together, they immediately try to do something else, and this results in light being emitted. This in no way diminishes the electrons. You get your photons or whatever, which in a lot of books are described, they say are a particle or a mass in itself, which I don't really know for sure, and I'm a little bit skeptical about it. But I don't see how you could, if you have a particle given off, that you'd be diminishing the electron. But that doesn't occur. Okay? And the charge, of course, is negative. Anytime you have an electron involved, you don't really have a choice. It's going to be negative. Okay? And we discussed about the fact that the movement is not a circular movement in the manner which most of the books describe it, but it's sort of a closed, lazy eight sort of thing that's compressed in on itself. And this also happens to be the symbol for infinity. And then also the infinity symbol was put in effect probably in biblical times. So I wonder what the connection between the infinity symbol and electron, which goes essentially forever, would be. Something that's producing energy, electrical and magnetic energy, and it does this continuously over billions and billions of years and is in no way diminished. So how come it does the infinity symbol? If somebody has an idea, I'd like to know. Okay. I have a different concept of how the forces of nature operate, and I believe that we mentioned that it's composed essentially of a weak force and a strong force, and that in addition, each of these forms of energy occur as fields and waves, depending on what the resonant frequency is at a particular level. And both of these have their own separate set of circumstances, and they are parallel to each other. For the weak force, for example, you would have your gravity, you would have your electricity, and you would have your magnetic field that would the weak force would emit. And that's, of course, from your electrons. Now, if you get over into the strong force, you're into atomic energy at that point, because you have to tear the atom up in order to get the center out of it. If you absolutely insist on a positive electrical charge, which some people call it antimatter because it cancels out the electrons. If they cancel each other out if they get in the same boat at the same time. So in the strong force, it's the one that controls the universe, and it's the clock motor that runs the universe, so to speak. And the weak force is the one that you could compete with on a daily basis. It's the one that you really have to be friendly with. It's the one that's going to be doing your work for you. Okay? And unless these particles, electrons, unless they're dislodged from their source and free to move about, which there are immense quantity of these electrons available to you, and the source is the sun. The radiation from the sun throws these things out, and they're part of the solar plasma. And when the Earth passes through the solar plasma, the magnetic field of the Earth pulls these electrons in immense amounts. It's equivalent to, I'll give you some numbers in a little bit on barrels of oil equivalent and other things, but it's astronomical, and this has been going on since the beginning of the Earth. And all of these electrons have been accumulating with nowhere to do and nothing to do and nowhere to go. And they're just sitting here looking at you. Now, some of the people, there's a book called, I think, Sea of Energy, Maury, and there's a number of other books where they acknowledge the idea that we have a huge envelope of electrons, corona-like effect of electrons, which surround the Earth that go up hundreds of miles. And you can tell how far they go up because where the light begins to form, the impact of the Earth passing through the solar plasma, the electrons of the Earth are banging into the electrons which are already out in the solar plasma. And when those electrons get too close to each other, they form visible light, and that's where your daylight comes from. It's electrons that have gotten too close to each other, and they're trying to get away, and when they do, they give off this visible light. So when you get out into the universe proper, there's no reflected light out there at all. It's just as black or dark as things can be, and the only things you see are other bodies that are electronically active out in the distance where the electrical forces are reacting, and they give off light, give off a point of light that you can identify. Okay? Okay, we talked about the fact that the electron itself is an excellent example of overunity. And just as a few moments ago we were saying that it goes through these cycles billions and billions of times over long expanses of time, and is never diminished. So if that is the case, then it is producing energy which is greater than what's there or appears to be there, and therefore it is a excellent example of an overunity device. If someone wants to tell you that they don't exist, well, the electron is probably the most obvious one of all. Okay? Okay, and we talked about the fact that the induction process itself is an excellent example of overunity due to the squaring of the cycles per second. And we also talked about the fact, I believe, that mechanical advantage is not considered unusual when it comes to pulleys or levers or gears or things of that nature. But if you use a small amount of energy to extract a larger amount of work, regardless of what the books say, haven't you got something back more than what you put into it? The physics books don't agree with what I just told you. Yeah, well, think about it. The physics books are wrong. It doesn't. The idea was set up back in 1670 or somewhere back like that, and a lot of the actual mechanical age hadn't occurred at that point. The machine age was still somewhere out in the distance. And so was the electronic age. So it's not very likely that somebody wrote a set of physics rules, say in 1670-something, would be able to compete with something that comes along later, which they had no way of ever knowing about. So think about that for a while. Okay, another way of looking at this would be that if you take a room full of ping pong balls and you get them all going in, many directions, and they're bouncing around, there's a certain amount of energy in that room. But if you line these ping pong balls up, and you can do it magnetically, and then all of a sudden you've got a tremendous amount of energy that was not present before. And this is what resonance is. It's what superconductivity is, and that sort of thing. So, and that's over unity. And the books won't agree with me on that, I can tell you. Okay? Okay, we're just about to the end of this. And basically, electrical energy is achieved when electron density at a point A becomes greater than electron density at point B. This is your potential difference between 2 points. And if that doesn't exist, you don't have any energy, regardless of how many electrons are there. It's just like the high pressure and low pressure areas in the weather system. Things are going to move away from the high pressure area into the low pressure area. And the electron's density acts the same way. Okay? Okay, some of the benefits of this particular system are some of the points which might be made are the electrons which cycle through this system after being used are returned intact to their former state for future usage. This ought to delight the environmental people. Okay, electron spin causes current and magnetic lines of force. The effect of current results from unequal distribution of negativity. That's a restatement of something I just said a minute ago, the electron density. Okay, the system is an extension of present technology. It is a spin-off or extension picking up and going forward with Tesla-type devices. Okay? And the system can use magnetometer studies for locating areas of greater electron density, or the fact that one is more dense, has a greater density than another one, in the event that you want to do your electricity between the 2 points. For example, if you put a contact on top of the Cheyenne Mountain out here, and you put one down at the bottom, and you ran a wire between the two, and you left a place there where you could plug your device into it, you would have about over 5 million volts of usable electricity there that would essentially have the same as 5 million amperes, because your resistivity would not come in, or your amps would not come in there after the fact until you put a load on it. At that point, you would know how many amps or whatever you could push, and they would be at the beginning essentially the same as the amount of voltage. So that's the reason why you can't run a cable between the 2 points and do exactly what we're talking about there, because it would vaporize. But there's other ways of getting around it. Okay? The system, I call my system Earth Electrical System 2, EES2, and this was the name that was given by the Department of Energy. I got into fisticuffs with them over it, and the political elections came up, and at the very point where they were supposed to sign their name on the check, well, they went sideways on me. And so basically all I got out of them was a name for it. That was the name that they assigned it for their files, Earth Electrical System 2. Okay? The system utilizes a non-polluting energy source. So if you want to look at the pollution effects, you've eliminated internal combustion engines. You've eliminated coal for generating electricity. You've eliminated just a whole slew of things that are poisoning the environment. Well, I think the state of California might like that one. Okay, the system utilizes a universally available energy source. There's no place you can go that you won't be able to work it. Okay? And you could anticipate that areas who have pollution problems, like Mexico City or Tokyo or Houston, Texas, or wherever, would like to get in line maybe to certify this thing as being their preferred way of doing their energy. So it has some very interesting possibilities. Okay, we have one other part to this, and then we're ready to go into the coils. Okay, let's see. I think we've already covered this. Okay, that completes the speech part of it. And I think at this point we can start thinking about coils. We had some coil guides done, and I don't know who has them or what. Do we have the printouts for the coils that we were going to hand out?
Well, we put all of the printouts and everything in the bookstore, and they get them for a couple bucks.
Is it still open?
If it's not, they can get them in the morning.
They'll be open till 10? Okay. If someone would step in there and ask them for those things, we'll pick up on the coil.
They're set up to sell is what they are.
They're selling them?
Yeah, they're selling.
Are you talking about the books or the coil builder's guide?
The builder's guide and,
Okay.
and your paper are both of them.
Okay, well, it turns out I don't have a copy of it here, so I'm going to have to wing it if I don't have one to look at.
No, we got one.
Just so happens.
Okay, I'll get it back to you in just a moment. Okay, let's see. Do we have some markers where we can mark on these boards a little bit here? Right here? Okay, and these are the ones where I can wipe them off. And I'm going to pull this back a little bit because as long as this day's been, I'm liable to step off the edge there and never know it. Okay, I'm going to draw you a diagram of actual working unit that was presented on the device this afternoon that you saw. Okay, I'll do it with a block diagram first, so it'll be real simple, then I'll do the individual components. Okay, what you need basically is a power source. Whoops. Okay, and that will be a battery. It can be anything from, say, a 1.5 volt battery up to, say, 12 volts or anything you want it to be, just about. And you can control your output somewhat by the amount of voltage that you're putting into it. Okay, the next item which shows up in this would be, in our case, we have simplified it. We go into the Tesla coil part, but I'm using a laser module which shows up in the Xerox machines, and it takes care of the step up in the voltage for you. And basically going into that, and then from that we're ready to go into L1 out here. Okay, this is your tickler coil or the kicker coil, or it's the one that's going to set things up for you so the other coil will know what to do. And say that you have over here 12 volts. Okay, it comes through this device here, and say that it's coming out 8,000 volts. And immediately someone is going to say, well, that's 8,000 volts, and it's at, say, 30 microamps. So there's nothing there. Okay, as we found out from Ohm's law, when you get into this type of device, that dissipation, ohms and amps are dissipation, and they're after the fact. So if they're putting microamps in here, it's simply telling you the amount that's being thrown away. It's not telling you the amount that's there or was left. This is the 12 let's see, 30 microamps, okay, is the amount of dissipation that occurred when it went through that step-up coil. And that primarily occurred due to the resistance of the wire. The wire in this type of device is about the size of your hair, and there are many, many turns to it.
Now, what is the second thing?
Ma'am?
What is the second box?
This one right here?
Yes.
This is a laser module.
Power supply for a laser?
Well, they show up in Xerox machines. They show up in laser printers. They're a little high voltage module. They show up in all kinds of interesting electronic devices. It's any type of device that needs a high voltage source.
What frequency is it?
It might, something very similar to this may show up in your bug zapper or your electric fence or all other kinds of devices that work on voltage step-up, yes.
What frequency is it?
What frequency?
The output.
Okay, the output frequency is going to be determined by the length of this wire right here. The highest frequency that you have represented in any of the components is going to be the dominant frequency. That's going to be set by the length of the wire, huh?
Is that then a little high voltage DC supply?
Well, actually, in the laser module, you're correct. Actually, you have one output, and then you have the ground deal here. In some of them, this ground deal comes back. Here's your input over here, which would be, excuse the expression, plus and minus. One is higher, greater negativity than the other. So this comes back, instead of being earth grounded here, will come back and ground into the so-called plus deal.
So would it be possible to use a coil from like one of those disposable flash cameras?
Any step-up coil. It doesn't have to be a laser module or anything else. I'm going to show you just a little bit examples from automobile transformers and a number of other sources.
I was more concerned with the output because most of those can't put out more than 400 volts.
Well, yeah, I have them that put out 30,000 volts, and then you triple it from there, and then you're just then getting into the L1 coil, and then you take it from there. So this is going to be our L1 coil here. Or,
Is the voltage output from the laser module area, is that critical? Or?
it's not critical. In any event, you're going to have more voltage than you want. There's almost no way to do this and have the voltage that you really want to end up with, unless you're wanting to make big sparks. And that's not the object of what I'm doing. I'm trying to tame it and bring it down to where you can do something with it which will be useful.
How many turns on your L1?
Okay, you get into a division or multiplication situation. So once you know the length of the wire, you know what frequency you want to run it at. Well, you cut that wire so that it matches the wavelength of that particular frequency, and then your inductance and capacitance will take care of the off and on deal, which you would expect the spark gap and some other things to take care of. So you put, say that you have coming into it, for example, say 8,000 volts. We just let that for convenience purposes. Okay, we put 4 turns. Say that we put 4 turns over here, 1, 2, 3, 4. Okay, you divide 8,000 by 4, so each turn there will have 2,000 volts on it. Okay, the next coil that we want to do, we can put 1 turn or we can put hundreds of turns. But what we want to do basically on that second coil, say that this piece of wire here is at 4 point something feet, which corresponds to 220 megacycles. Okay, whenever you get into wave type arrangements, you have half waves, quarter waves, eighth waves, and so on and so on. So basically what you want to do on any turns or whatever you put on your second coil, they should be a relationship such that it will be either a multiple or a division of the same frequency. The second coil is going to run at a different frequency because the wire length is different. Coils are actually antennas that have been coiled for convenience. They work just fine as a piece of wire. But when you start putting them winding them, you're doing that more for convenience than anything else, and it's going to change your inductive characteristics and a number of other things, but it's not going to be detrimental to what you're doing. Yes, sir. I thought I saw someone with a question. Okay, once you've got this thing divided down and you've got 2,000 volts on each turn here, then you're ready to go to your L2 coil, which will be the second one. In many cases, that is going to be a great many more turns than the L1 coil, but it may be one turn. So if you want to, say, 2,000 volts, instead of a great deal more, then you've made just one turn and make it so that it's a division or a multiple of from the length of the other coil, so that they will react from a frequency standpoint properly. Now, you can get computer programs where you can figure these things all out on the computer, and you'll end up with the same answers. If you do it the way I'm doing it here, you can do it off the top of your head, and there's really very little mathematics involved. So it's not that complicated. As I mentioned earlier, this is one of the things which I teach the Cub Scouts to do. So if they can do it, you can do it. If you got them and you give them, you've got a group of these kids and you give them the parts and tell them what to do, and they do it and take it home and say, Dad, here's my over-energy device. Okay, we've gone to the next step here and say that we've got one turn, and on this deal, it makes one complete circle here, and it's has to be grounded in order to pick up the maximum effect of the electrons. And in order to ground this thing, see, we've got two different coil sets there. Now, anytime you add a capacitor or any other device or resistor or anything else into this circuit here, it's going to lower the frequency, so the highest it can be will be based on the length of the wire. And then if you add something else to it, well, then it's going to lower the frequency. Okay, we've got two coils, and they may be very slightly out of tune, not precisely tuned. So you need a variable device here, which can be a variable blocking device, which can be a variable capacitor, or it can be a variable resistor, or a number of other things. And you have to do this by experiment, and don't put any real heavy resistors in there. I mean, any high resistant deals, put some that, say, like down below 500 ohms, maybe around 100 ohms or something like that. And this is going to be that shunt that's in the resonant circuit that we were talking about a little bit earlier. And it's going to be the dam that's going to hold the water behind it, so to speak. Okay, at that point, we've got 1,000 volts in a radio frequency setup, which is absolutely useless unless we do something else to it. So at this point, it's not an eraser, is it? It is? Okay. Well, it works. Okay, we're going to pick up where we have the one turn here, and we're going to take it on to the next steps. We've got one turn here, and we've got it grounded with a variable device on it so that we can fine-tune it. And at that point, we've got from this deal, we've got an output out here, which is in an oscillating type, alternating current type situation at radio frequency. Yes?
One quick little note there, that ground symbol, could that an alternative be the negative of your?
Yeah, that is the shunt in the resonant radio frequency configuration that produces a dam that keeps the energy. Once it gets to oscillating inside the system, if it can come in, but it can't get out unless it is hooked into another system.
I guess what I'm saying is whatever L1 ground is, or if it be an earth ground or the common, that's what you're referring to.
Yeah, well, it's simply a blocking device which keeps your resonant coil system, which normally you have a capacitor and a coil, and you've got them like this. Well, in our case, we've put both the capacitor and the coil in one wire, and we've eliminated some components that are subject to fail. When we do that, capacitors are subject to fail, so you've actually made a device which is less likely to fail. It has greater longevity. So anyhow, we're going to be throwing pieces away as we go through here and see how we can still end up in business. Okay, we've got 1,000 volts here, and it's a radio frequency, and we need to get it into conditions so that we can run something which is 120 volts at 60 cycles. Oh, yes, sir.
Just to clarify, L1 ground and L2 ground are
Well, they're grounded in different ways. L1 grounding can be grounded back into the laser module itself, or it can be grounded into the earth or into the same common ground that L2 is actually grounded to. You'll notice in the Tesla coil books that frequently both those coils have the same common ground. Okay? Okay, we got 1,000 volts, and we're going to go to a lower voltage, which we can do something with, at a waveform, which we can do something with. So at this point, we're going to have to go through a diode bridge. Let's see. Okay, we're going in for the alternating current, and we're coming out to DC and DC. Okay, at this point, we've got something which we can take through one or more steps, and we're where we want to be. We're very close to where we want to be. Okay, we take off from the DC here, and we come out like so, and we're going to inject a coil in here, which is actually 2 Tesla coils, bottom to bottom. This is the middle here. This would be the base of a small Tesla coil, and this would be the base of a small Tesla coil. At this, yes, sir. I can hardly hear you.
Do you have the DC to AC?
Yeah, we've got DC coming out here, so we've got to pulse that in order for this coil to work. So what we do, we put a capacitor in parallel there, which gives a pulsing effect or an off and on effect, which will cause the magnetic field to be, or induction to pick up in these 2 other coils. Do what?
I think what he was referring to is your bottom end of your AC. You're hooked up into the bridge. Into the
Well, actually, I'm trying to get around that. Let me come across here and do that sort of thing. Will that be better?
Okay, now the other one?
The other one, I got to do the same thing. I got to lump it in order to get over there.
Both at the same point.
Well, I'm going to have to erase it and start over. I'm going to do it on a larger scale. Okay? We'll do it on a larger scale where I can get my lines in there properly. Okay, we've got our diode bridge here, and we've got AC, and we've got AC, and we've got DC and DC. Are we okay so far? Yeah. Okay, we're going to turn these diodes so that the cathode end of it is pointing towards DC right here, and we're going to turn this one so that the cathode is pointing towards DC. Okay, the two coils, the two here, the cathode is pointing towards the AC, and here it's pointing towards the AC. Does anybody know why we do that? What we're going to end up with is basically a SPAC, a DC. A DC, of course, if you've got your reference point here, you've got alternating current, which is doing that sort of thing. Okay, in DC, you're going to be on just one side of that reference point, which will be the top side or the bottom side. And you're going to be on just one side. So at this point, the waveform coming out of here is going to be a DC SPAC. Okay, and we're going to change that. When we go through this thing right here, that's going to change to, say that this is 1,000 volts up here. Okay, we've got a DC SPAC with 1,000 volts on it. When we go through this system here, we're going to have a DC SPAC above and below. It's not going to be DC anymore. It's going to be alternating current. And it's going to be double the voltage that you had here. So we've gone through a voltage doubling maneuver here. And we're coming to the waveform that we're really looking for now. We're getting very close to the waveform that we're going to need in order to run our 60 cycle device. Okay? Okay, and this double Tesla coil thing here has a variable blocking device on it, and it's grounded. Two bases of the Tesla coil are grounded. The top of each Tesla coil will be these ends right here. Okay, at this point, I'm going to have to race this in the center because I'm going to superimpose something. Okay, you just have to keep in mind that you've got a double Tesla coil there that's oscillating, and it's forming a double SPAC deal, which is very close to what we're going to go for. Okay. I'm going to turn this around a little more. Okay? Is it safe to say that everybody can see it? Okay. Yes, sir. There are 50 turns on each end. The diameter of the PVC that I wound it on is 1 inch, 1¼ inches. And there's 50 turns on each end, and add an extra 2 on one of the ends. And the reason for that is that you want one end to be delayed just slightly more than the other, so that you're going to have an offset on those spikes when you see them on the oscilloscope. Did I hear a question? Okay, on that coil, we've got 2 spikes, one above and one below now. And we're getting very close to the waveform that we're going to be wanting. So at that point, we assume that the grounding and other things and the bases are still there. Okay, at this point, we've got 2,000 volts. 2,000 volts on this arrangement right here. Okay, now say that we want 100 volts instead of, I'm going to round it off instead of saying 120, which is going to create a mathematical problem shooting from the hip, so to speak. So I'm going to say that we want 100 volts. And in order to do that, we need 20, let's see, divide 100 into 2,000, and we need 20 turns there. And what we're going to do is come in from this side with a piece of wire, and we're going to, it's going to be loosely looped around this. It's going to be very informal, and it's going to come off like this. And once we're off out here, then we have another wave shaping maneuver that's going to occur. And at this point, what we want to do is round those spikes off so that we get what we're looking for out here is a normal sine wave thing. And we need to delay the time a little bit there so that when it's up at that top there, that it's going to spread out in this top area. And when we do that, we end up with this type of thing. Now, we're at the waveform where we can do something. We've got 100 volts, and we've got the proper waveform. Now, we're at the point now where we're going to set the frequency. And there's going to be another maneuver at this point. And basically, this is where we go back into the over unity thing. So over unity people will be happy about that maybe. We're going into a resonant iron core transformer system, and this is where we're going to end up with all the amps and the other things that the electrical people would like to see maybe. So say that we go into an iron core transformer here, and we're working off of it. And this device is going to, it's self-resonant transformer. It's a self-resonant isolated transformer, which means that the other side of it, which I'm going to put up in a moment, is not connected in any wires. The only connection is through the induction. So we're running it through this thing that's going to set the 60 cycles at this point. Okay? And then we're going to take the one which we're going to come off of, and here's where a load is going to be added. This is where the wall plug in the house is. So we have a magnetic flux field on this one, which is driving this one, and the self-resonance of that particular transformer is 60 cycles per second. And I've got one over here on the floor I can show you. It works at 4,000 volts. It's a real heavy looking, kind of block of iron looking deal. Let's see. Yeah, that's it. Okay, this one is good for 4,000 volts. You see there's two different sets of coils here, one sitting on top of the other. This is an isolation transformer. And
One to one?
do what?
Was the ratio 1 to 1?
No, this one is, the top coil is set for 4,000 volts. The bottom coil is set for 2,000 volts. So in our case over here, both coils are set for the same. So you can either step it up or step it down. At this point, you can, depending on what kind of output you want. If we want 440 or 6 whatever, or 220 or that sort of thing. So if the two units are equal, you will end up with an equal amount of, say, 100 volts. Sir? How did you guess? Well, the price is right. That's what it is. I had a neighbor who was an electrical engineer who knew what I was doing, and he and his son switched out their microwave oven, and they were curious as to what was inside, and after they tore it apart and found this thing, they came bouncing over to my house and said, well, we think you need this. This was about 6 months ago, and I didn't know that I needed it. But whenever I got to the point to where I knew that I needed to do something like that, well, I realized I had this thing out in the garage, and rather than go out and spend $400 buying one, I already had one. So this can drive a very substantial output of electricity.
Question, how can you be assured that it's going to make exactly 60 cycles?
Because the resonance is built into the transformer. You don't see it here, but there's a capacitor that goes with this. You see, this has a certain amount of induction, and there's a capacitor that you put with it that forms your resonance circuit. Okay?
In series or in parallel?
Well, in this case, it's in parallel. Almost all the things that going here will be essentially in parallel, because when you put them in series, you get a degradation.
Would it be on the feed side or on the load side?
Where is this? Okay, if we're talking about the one that we have here, we have 4 sets of wires. You notice that with these little snap-on deals here?
Yep.
Okay, well, those are the output deals, and these other wires, these 2 heavy ones, are the input, and this is the grounding.
So you put the capacitor in parallel?
It's going to be in parallel
On the input?
on the input. Okay, at this point, we've got our 100 volts, we've got 60 cycles, we've got the correct waveform, and we're in business. Yes, sir.
On your back-to-back Tesla coils, how many turns did you have?
There's 50 turns, and on one side add 2 additional, which gives a delaying effect on the second SPAC there, so that you get an offset on it.
So you have 50 and 52.
52 on one end and 50 on the other. It doesn't matter which end. Huh? Go ahead.
And the Tesla coils are wound in...
One is wound clockwise, and one is wound counterclockwise. And that is part of the slowing down of the electrons, so that you end up with the waveform that you want. Okay? Go ahead. Over here.
Are you going to demonstrate the system now?
We will see in just a little bit.
Yeah, I had a question. You had the primaries together on the back-to-back Tesla coils.
Uh-huh.
Then that coil that's going through the isolation...
Well, remember now, what we're working with is a DC SPAC going into those things, and what we're trying to do is get rid of that DC SPAC.
Yeah, my question is that coil going to the isolation coil is in addition to that. So that's the third coil around that. 20, is that right?
Okay, tell me when I get there.
That one, yeah, that right
This one right here?
The 23 you have in the center.
The 20 turns in the center is it's lowering the 2,000 volts. You've got a transformer there.
People with questions, I'd like you to step up to the mic because you want to get the questions on the video. We can't hear you fast.
Okay, by keeping this sort of informal, it'll make it a lot easier on me. This is the wrong time of day for me.
On the Tesla coil, is that close wound?
Close wound?
On the
not
2,
necessarily
on the 15,
so,
52.
because you get a lowering and you get your Q factor messing you up a little bit, but the induction on this thing is so strong that you're not really having a problem. Yes, sir.
What's the amperage of the load?
The amperage of the load, it will be the same as the voltage until you put a load on it. And once you put a load on it, that sets your amperage.
I don't get it.
That doesn't make sense to you?
It's on that.
Okay, earlier you probably weren't here whenever we talked about it, but ohms and amperage are after the fact.
Right.
And it's not until you put the load on there, or the resistance, or the dissipation factor, that you have ohms and amps. So you have 8,000 volts or 2,000 volts or whatever, that's how much you've got, and you have potentially the same amount of amps as you have volts if you work it correctly.
So you can run anything.
Sir?
You can run anything.
I couldn't understand.
You can run anything.
You could run just about anything you want to. The one of the units I had up this afternoon will run a diesel electric train. You can disconnect the diesel part and put as many coaches on it as you want. And that unit, the induction, we were talking about the induction rate being so much higher than 60 cycles. Well, something millions of times smaller can produce the same amount of electricity as a very large 60 cycle generator. So that small unit would produce the amount of electricity that a conventional generator the size of this whole room would produce.
Can we see it?
You want a demonstration? Okay, you bring me the train and we'll do it.
How about an arc light?
An airplane? Yeah, we can fly a DC-10 if you want to.
I wonder if you could just...
Let's see which units I've got here and whether I've got a unit left. It looks like some of the units are missing. Was in there?
I've been watching it all night.
Now there's some things. Excuse me. There's 2 devices which are in the office in there, in the bookstore. Yeah, the 2 that I need right now. Yeah, well, somebody in there knows that this is the stuff we brought in from the automobile. While that's going on, let me get something here, and I'm going to show you. Excuse me. I'm going to show you how this induction stuff works.
I'm wondering if you could quickly comment on the size of wire that's been used in this so far in the coil.
When you're working at radio frequency, you'd expect at very high voltage to have very large wires. Okay, that is very true if you're down in the lower frequencies. But when you get up into the radio frequencies, the diameter of the wire can be very tiny. It has to do with the size of the electrons and how they're spinning around and that sort of thing. So you can have a wire that's about the size of one of your hairs in your head, and you can have basically 1,000,000 volts on it, because the electrons are not going through the wire, and there's no dissipation factor, and they're spinning on the outside of the wire. So you can have this corona effect. See, I told you they were somewhere else. Okay, just put them on the table here, and whenever I get to them, I've got some magnets here which I want to demonstrate something for you. See, how much voltage would you think it would take to penetrate a 1/4 of an inch of PVC? It'd take a lot of it, wouldn't it? Maybe even 1,000,000 volts. Okay, what I'm going to do here, I'm going to show you how the magnetic effect, it varies from Okay, your induction is from magnetic effect. So you could take these wires, they can have a covering on them. They can be encapsulated. You can put them in solid concrete or plastic or anything else inside, completely insulated from everything. And these wires, when the induction effect starts taking place, which is magnetic, it doesn't see any of it. So that's why your induction works so well. And that's going to lead us right into what you were asking about. Everybody see that? There's magnets inside and on the outside. And that's the magnetic flux thing that we take a reading on for these maps that we were looking at with a Gauss meter or other kinds of magnetic flux devices. We can, by the reading, we can directly convert into the active electrical energy that's present. Okay, at that point, before we get off on this device, now there's a little lunch pail-like thing over there somewhere, and it may be back in the office also, and it's got the battery for the device. It's a little lunch pail thing, sort of interesting colors. You can probably tell who it was designed to sell to by the colors. That wasn't a very nice comment, was it? Okay, I'm going to show the battery. This is a calcium lead or lead calcium battery, and it's 12 volts at 7 amp hours. Yes.
Oftentimes called a sealed lead acid or a gel cell.
Okay, that's good. Anyhow, in my experience with this device, when I hook it up to it, it turns out that the L1 coil on this device has a 4-point-something feet of length of wire. It turns out that the wire which hooks onto the battery here has that same length. we're dealing with a radio device. So we've got an L1 there, which is oscillating at the same frequency that this wire here that goes to the battery would oscillate at. So guess what? When I hook it onto this battery here, it's going to be generating electricity and feeding back into the device, and it's not going to be using the electricity out of this. And how I know that? These devices have been ran for as much as a month at a time, and with no lowering of the capacity of the battery. So if you're looking for an over-unity device, you've got one right there. And there's other ways of making it do the same thing. There's also a thing called a capacitor battery, which is a new invention which is on the market just this year, I think. It shows up in some of the computers and other things, and basically what it does, it stores electricity so that if the source misses a beat, it picks it up and keeps things going. So by putting a capacitor battery in parallel on these input wires here, you have an additional kick which would do the same thing as the wires were doing on their own. So if the wires were not the proper length so that they would pick up the radio frequency energy, then you would have your over unity type device in one case. In the case if the wires were too different length, you wouldn't be getting that feedback. They have to remember they have to be a multiple of or division of frequency which is there. They don't have to be the exact length. So if they had been 2 point something instead of 4 point something, that would still be a division of the frequency, so therefore it would still have worked. But with the fourth thing, you got more feedback. And that's one advantage of operating up in the higher frequency, because if you were run down below 200,000 cycles, this cable here would have to be maybe 400 feet long to do the same thing. So in the frequencies which I'm operating, it works very well, and it had a surprise effect which I only discovered after a certain period of time. I knew that something was wrong. My batteries were never running down. And the books tell you that that can't happen. So here I'm looking at the silly thing, and you're doing something you're not supposed to. What is it? But it turned out okay. And with that, that sent me running to the patent files to find out if there were any patents that related to that sort of thing. And there was a thing, I think it was Baldini's magic battery. Back in 1946, there were a lot of articles appeared in the newspapers throughout the United States about this magic battery that would never run down. You didn't have to charge it, but it never ran down. But they didn't bother to tell how it was accomplished. And in my mind, there had to be some sort of thing happening similar to what I was doing in order for that battery to function the way it was. But it turns out that it was never patented. There's no patent of record. And whatever became of it, I don't know. Somebody apparently bought it out in order to keep it off the market, or paid the guy, a few $100,000 or something, and was able to stick it in a file somewhere and keep it off the market for some business advantage, whatever it might be. Okay, with that in mind, I'm going to hook this thing up, and we're going to see if it works. It's been bouncing up and down the road. It was in the back of the car from Houston, so we will see whether I've still got a device or not here in a second. But they're pretty durable. There's not much here that can go wrong. Okay. There's nothing unusual here that you can't find down at Ace Hardware or at at the local level. Radio Shack. Radio Shack, I should own some of their stock.
What is the gauge of that wire here?
This wire here, this is, if you recognize it, it's what's in your chandelier at home. I simply pulled it apart. I thought with a gold tint on it, a transparent gold tint on it, it looked nice. That's what determined what I used. Well, that is probably correct. But it's a normal lamp cord. And with this in mind, we have to be very careful when we hook this thing up, because the laser device there, if I hook it up wrong, I've blown it. You have to get your plus and minus in there correctly, or you've lost your device. And if you go to the store to buy these laser modules, they can get very expensive, or you can find them at surplus places, and sometimes you can get them at a very nice price, if you're real lucky. But, sir?
There's a company called All American Electronics, which is surplus.
Okay, well, if you just happen to luck into it, you might get them at a very reasonable price. But if you get caught in the market and you pay the full price, what you're looking at there is about $300. And you can wipe that out so easy you can't believe it. If you reverse these two things, that's why the colors are on here. And you'll notice down here where they go into the block, they're also colored. And you'll notice on the battery, they're also colored. So you get into this situation where you try to idiot-proof what you're doing. So if somebody is going to be duplicating, yes, sir.
Got a question for you.
Surely.
Why don't you just solder your bridge diode on there for protection? That way, no matter how you hook it up, it's right.
There is a diode right here. And this is the kickback protection right here.
Okay.
It's a little tiny diode that comes from Radio Shack. You get about 50 of them for 50 cents. Okay, if this thing is working properly here, you see these little bean-looking deals that are on the end here? These are 60-watt neon bulbs. And they've got a resistor on the deal here, so that we're working with radio frequency, remember now here, so we're crossing over, and we've got a radio frequency device. And we've got these little bulbs that are built in various parts of the circuit, so it'll tell you that it's working up to that point. So with that in mind, let's see what we've got here. Okay, something's not functioning. These things should light up. And no, the battery's not. It's been sitting out in the hot, though. Would that mess it up?
Maybe the earth stopped.
Do what? I've never had one go dead on me yet. And it was fully charged when I came. So basically what at this point, we'll learn how to fix one, I guess.
Someone sacrificed their car battery.
Well, there's only a couple of things that can go wrong here, and we'll find out real quick. Like, let's see, let me make sure that I get these on correctly. Okay, what we're going to do is check and see if we're getting our voltage up to this first point here, and which we are. We've got 12.94 volts there. Okay, what that's telling me immediately is that this little diode here is out. And if you want to suffer with me, we'll change it.
We'll suffer, do it.
Okay, over in those little plastic boxes, you'll find a whole bunch of them. No, those are lightning arresters. These are little tiny things. They look like. Well, no, we just determined it was okay. They're little tiny things. They look like a little hair or piece of wood. That's them. That's them. And I need a screwdriver and one of the little flowers, that little black flower deal there, and a screwdriver. Okay, we're not that bad off. We're going to have, it'll be operating here in about 2 seconds. And meanwhile, I'm going to undo this. Let's see, you're standing here. You can get it out for me. And while you're doing that, well, I'll be shaping one over here to go back in. Yeah, it's disconnected. Yeah, we're going to be just fine here. This is not a terribly unusual thing to happen, but actually we can put a different kind of diode in here, and it probably won't happen very often, but the fact that it does happen has saved us our laser module. And basically what you need to do there is get these legs under there, and you tighten them up, and you need to turn the ring so that that ring thing is pointing that way. Yes, sir. Okay, we'll go to that in just a little bit. Let's do this one and see what happens, and then we'll go. I'll show you how we get through those different stages. I've got the parts here. Okay, to see the little rings pointing the other way, isn't it? Okay, we should be in business. If these lights light up, you know that we got there. If they're not lighting up, on a radio device, the energy would be hitting me and running off. Now, the only other component that can fail in this thing would be the spark gap here. So somehow or another, something has touched this thing and got the spark gap out. Let me undo this. And yes. Okay. Here you've got your 12 volts. It's bad. It's bad also. Well, I think that's the cathode is the ring, isn't it? Is the
Disconnect the diode.
you heard it? Okay, if we do it without the diode jumper there, tighten it. Okay. I thought I saw a flash here for a moment. It's not coming through, or that thing will be flashing. I saw a spark there. When it flashed, it probably burned, so you need another diode. Those were in it when I brought it, so someone may have been playing with it before I got here. Yeah, these are the ones that I use. Well, they don't. That's probably why they blow. Actually, I need a larger one, but I don't know exactly which one I need. Yeah, well, these will work for a period of time. Okay. Okay, let me do that. It's in there to prevent kickback and destroying the laser module. Can you use two of them together? Yeah, well, I was going to get some 4000s and I didn't get there. If you move that wire over there, you're bypassing the diode. But we can do that. I can. Oh, okay. Oh, okay. Is that 4,000? Yeah, yeah, that's all. Yeah, well, now you're going to give him a thrill. Okay, is it okay to... You want me to turn the battery on? Okay. It turns out that the diodes that we're trying to put in there are no better than the one that we took out, which was bad. The device itself doesn't really have anything wrong with it. It's a safety diode that was in there to protect the laser module that was burned. Yeah, well, this is one I was using, which is obviously too small because it should be 4000 series.
4148 is the newer replacement of 914.
Okay, well, let's write him on the back here for me, and I'll get some. Yes, sir. This puts out enough energy to drive a diesel electric automobile. I haven't yet because it has been my show and tell thing, and okay.
There's a series, and I'm like maybe a
41,
look it up, maybe a 4149.
Yeah, I'll look in the description book.
We're right by.
Okay, if it's working, these things are light up. Okay, it's not plugged in. That's
Right.
okay.
Sit down,
By
please.
the pool.
You see a spark? You see a spark? And oh, well, that's strange. It's too heavy a diode to be doing that, isn't it?
You need the diode.
Okay, it looks like. Okay, if it's blown up, it's blown up. Okay, in any sort of radio device, you'll have things that will fail on you, and there are relatively few things in this device, so there's only 2 or 3 things that could go wrong. I'm off. You tell me when you want me to go on. Want to turn down? It's on now. Let's see. It's on now. Is the spark plug yet sparking? There should be a spark. Well, that is one of the things that can go wrong.
I can see a gap in it.
There's a, yeah. If you have a piece of ordinary writing paper, there's the paper that's in that tablet there would work. There's a spark plug in this system which it doesn't need, and that is one of the things in favor of getting rid of some of the components that fail on you. Sir?
Is that a Bosch flex?
No, ordinary spark plugs are made to run for like 40,000 hours or something. So that is plenty long for... No, it's just an ordinary spark plug. And if it's running, these things will light up immediately. Okay, we're going to go to another device. This one, I'm having problems with it, so I've got another one over here, which we're going to have some fun with. We're not lost yet. It's one that's got 3 coils on it, and I don't see it here anywhere. It's got 3 coils about this tall on it. Yeah, well, someone go get that other one because it works. Okay? Yeah, it's real obvious. It's real obvious when you find it. It'll have 3 coils that are about 5 inches tall. Sir? Yeah, this what's in the office there was what I had in here for another deal, and it was not in the trunk of the car. So we've got everything. We don't have a problem. Okay, the one that I'm going to bring in now has 5, quiet please. The one I'm going to bring in now from the office has 5 1,000 volt lightning arresters in the circuit in place of the spark plug. And they're going to light up like a Christmas tree. So I've eliminated the spark plug and I've stuck lightning arresters in the circuit in place of it. I don't need them at all except to show you that the voltage is there and that things are going on. But for someone who's not sure these devices work, it's a cure for it. Yes, sir.
You said you're stepping down 20 times.
Yeah.
From 2,000 volts
to 100.
But L2 has 1 turn, and your pickup coil has 20 turns. So you're stepping up, aren't you?
Well, when you're talking about L1 and L2, okay, let me show you what's gone wrong there. This one right here is L2. This is L3 and L4. And out here, this transformer would be L5 and L6.
You've got a 3rd coil over there on L3 and 4.
Point me.
There's a coil.
Right here? Okay, well, we should say that is L5 then, and this is L6 and L7. Is that better? Okay, remember now, this is the wrong time of day for me, and I'm not functioning 100% here. I'm running about 20%. So if I do something like that, you want to tell me about it. Okay. Okay, while they're working on that one, we're going to bring the other one up, and I think we're going to have a very, very interesting difference in what's going on. Okay, and I'm going to set it so that it kind of sticks up where everyone can see it. I'm going to bring the battery over, and someone may want to, once we get this thing going, may want to lower the lights a little bit so you can see these things flashing. Yeah, they're working. Lower the lights until everyone can see those little lightning arresters working there. Okay, they were working a second ago. Yeah, I saw them when I first hooked it up. They were working.
I saw them pop.
Which one is that? No, because this one has no rheostat on it, see? Yeah, you can put them back up. I wonder if we have a diode that's bad on this one. It's the diode. Because the moment I touched it, I saw them flash, so I know that, yeah. Whoops. Let me hook it back up here.
This is only getting 2 volts.
So that would reduce it. I wonder why that is, because normally these things light up like a Christmas tree.
It's only getting 72 millivolts.
Oh, why would that happen? Check the battery here. I'm sure that unless the sun got to it, it should be good. Okay, you notice that there are 4 coils on this. The center one here is actually the one that's doing the work. And it's a miniature radio broadcast station. And it's putting out induction. And there's a small number of turns down at the base of it here. And then there's a certain number of other turns up above. And basically what we're doing, we're raising it to about, this is 8,000 volts going in from this module here. And we're running it through 6 turns there on the L1. So divide 6 into 8,000. And that's it's okay now, maybe? Yeah, it's going. Turn the lights down.
Down in front.
Is there 2? Okay, each one of those, each one of those lightning arresters there, it takes 1,000 volts of actual real electricity, not diminished in any way to trigger each one of those. So at that point, we know that our main coil system is working there, and we know that the outside coils are tuned to the same frequency. So if we have 40,000 volts on that inside coil, we have 40,000 volts on each of those outside coils. So this is built to show what an over-unity device in several aspects does. Now see the little 60-watt neon deal here? See? That's lighting up because of the radio frequency electricity that's running along my skin. That's actually 60 watts right there, and this battery is not putting out that type of deal. Sir?
Thank you. Can you put a bigger load on that?
You can put a load up to whatever the voltage is.
Could you do that? Can you plug the fan into it?
Okay, in order to do some wave shaping, actually we've got a situation here where we're going to be running the fan, but we're going to be doing it a little bit different than you think. But let me show you part of the components over here on what you're looking at, the actual device. Okay, this thing, you see the box is the diode bridge, and here's the system, but it's wound a little bit differently. As a matter of fact, I've turned this around backwards. I've got the windings on there a little bit different, but this is actually the mechanism that does the wave shaping that gets your double spike, that gets you set up for doing your waveform that you're really looking for. So this is one of the wave shaping modules. And the windings are, this thing is on there backwards. I've got it hooked up backwards. This is the resistor component, adjustable resistor component that works on the resonance circuit. Yes, sir?
Could you potentially run a home with one of these?
Run what?
A house.
Oh, yes. What we're looking at here is a great deal more than you would need for a house. Yeah, what you're looking at running here will run a large office building. Yes, sir. Oh, sure. It's due to the fact that your induction is working at a radio frequency which gives you your higher efficiency of induction that makes the small device possible, because it's doing millions of times more efficiency and output in comparison to what's going in than your 60-cycle device would be doing. So that means that it could be millions of times smaller.
You just wire that into your house panel?
Well, you have to go through the wave shaping and set things up so that it matches the devices that you want to run on it. And then you're home free after that. Okay. Yes, sir?
I don't see an earth ground on here. Is it?
It's actually grounded in a way that you wouldn't suspect. It's in the ground. In this case, it's inside the module here, and it's coming back through one of these hookup wires.
But how is it getting to earth ground?
It's ground. You can ground these things into the air or into the earth. You have a great deal more efficiency if you ground them into the earth. If somebody will produce a metal pipe for me, we'll ground it into the earth.
Yeah.
Try your microphone.
Well, we need one that goes down inside the earth. And that's what this is all about.
Why not use the center connector and a plug?
Yeah, third
Sir?
prong.
Use the third prong and a plug.
Oh, yeah, I know what you're talking about. I don't want to use the microphone here. Does it have 3 prongs?
The metal case of the projector is plugged in, so you should have a
Okay, I see what you're talking about. I wonder if I can pull it out far enough to...
well, no, it should be the actual shell of the projector itself.
Oh, okay, that's the metal parts? Okay, let's see. Okay, well, I guess we may have the thing solved. Well, it looks like somebody got to it, but I'm missing my hookup. Somebody's been helping me. I wonder who. But the idea is that you have a much more efficient system if you ground it directly into something that's into the earth. And you'll notice that on your fuse box at your house for the electrical system which you have. Well, if you want to. They're 2 different sizes, but I don't think that will matter. Anyhow, you wanted to see a fan run and some other things, I understand. Okay, before we can do that, there's a little square box over here that's kind of dirty looking. Kind of small. No, it's about twice that size. That's it. Okay, this is an inverter. And an inverter is basically what the circuit we're looking at over there. But this is one that came off the shelf. And okay, my gold cords. Okay. Let's see if we can figure out how to do this. It's going to be rotating. Maybe I can move this over a little bit. Oops. Okay. We're not going to be getting exactly the circuit that you asked for, but I'm going to show you how you can run a 300-watt device off of a 12-volt battery. It's basically what it amounts to, which would be equivalent of tapping in on this thing at this point. So I'm not going to be able to run it with this device at this point because you have to be hooked into this device, and there's another part that's missing off of this. But I'm going to show you how you run a 300-watt device off of a 12-volt battery through an inverter, which is what that circuit is there. Well, if you want to come up here and hook it up, you're welcome. Okay, the inverter technology is what enables you to do what we were talking about. And we have a, let's see, oh, I forgot to turn it on over here, didn't I? Okay, how's that for 12 volts? So if we can do that with 12 volts, what can we do with 1,000 volts with an inverter circuit? Now this inverter circuit, I'm going to draw you what's inside this little box here. There's a resonant iron core transformer, which we were talking about. This unit right here is the main component of that inverter. There is this unit here. There are two transistors which are back to back, and I'm going to draw you that circuit. And when you put those things into this circuit here, when you couple them into it, you've got the same thing going. You can get rid of the battery there. But they have to be adjusted to the voltage which you're working with, and that device there is only made to run with 12 volts. Let's see, I've got a... Sir? Okay. You know what? How about Radio Shack? And it was 89. You missed the point. You missed the point. Okay, just back up a second and let me tell you what's going on here. You weren't listening. We have inverter technology which interfaces between this device and any device that we're going to run. So that wave shaping deal that we were showing you over there, this device here with some other things added onto it is the equivalent of what's in that inverter there, except it's designed without the transistors. Okay, basically what you have here are two transistors, one on each side, and you have a resonant iron transformer in there which gives you your 60 cycles, and you have a couple of resistors, and that's the whole device. So what you do, you take that circuit and you convert it so that you can handle the output of a much larger device. So there's your inverter technology being adapted to work with the output of the test signal.
That off the machine
Uh,
Is the inverter running off your machine maker?
yeah.
Right, but the whole thing is...
Okay, one problem at a time. It's not, if this lights up, well then you can throw that one away. Yeah. Okay, what I was showing you there is the inverter technology required to make the other device work. Now, you ask why haven't I done that? Simply because there aren't enough hours in the day is the reason I hadn't done it.
You can't prove here tonight your system.
If you understand inverter technology, you have no problem understanding what's going on. Okay?
Mr.
I'll
Smith.
see you after school.
Mr. Smith.
Y'all need to be careful with this. Give this guy a chance. This was intended to be set up for tomorrow, and the tests were all going to be done. The machine was supposed to be working tomorrow. He did this impromptu. He drove all the way up from Houston. This stuff's been banging around in his car. He's not had time to test it out. So please don't be doing this. This is not professional. I understand we're all upset because it's not working, but there's a lot of things going on here that you see the wires are cut, the diodes aren't working, the laser power supply's blown. Give the man a chance, okay? Now tomorrow, if it's,
Well, it's unlikely, but there's something else there. If the spark gap is screwed up, or if any of these screws have gotten loose and bouncing up and down the road, we've lost contact. But we know that the basic idea works because this is the same device right here, except for those lightning arresters. your laser module, your L1 and L2 coils. Yes, sir.
Is there any way you can light your machine up and then do a test off it for output?
For output, if you have the proper instruments to do it with.
Do you have one here in your block?
I have some radio frequency devices which I can tell you what frequency these things are running at, which I can tell you that it will correspond to the length of the wire exactly the way I was telling you. But what you ask about there, I don't have with me. You need oscilloscopes and you need a lot of other things in order to properly prove these. And I have engineering friends at home. I'm not an engineer myself, and I don't have all of the devices that you need to properly test these things, but I have neighbors who are professional electronics engineers and other kinds, and they do have these things in their home workshops, and I do take them to their house and I do check them out, and I do know what they're doing. So even though I may not be able to demonstrate it to you right now, they have been checked out, and I know exactly what they're doing, and I can tell you. Yes, sir.
What about this box of yours that you ran the fan on?
Okay, that is an inverter deal, a commercial version that you buy off the shelf.
How much would you buy that for?
Well, this actually has the price, has the sales slip inside the little book here, and I can tell you exactly. It was bought in 1985, and in 1985 it cost $83.95. Yes, sir.
I'm interested in this ratio between the L2 and the L5.
Okay, every time you go through a change of coils there, you're either going to have a step up, step down, or you're going to have an isolation deal where the same amount passes through.
What I'm saying, L2 you have 1 turn, and L5 you have 20 turns.
Okay.
So that's
You're stepping down.
stepping up.
Well, you're supposed to, what we're trying to do is get it down to a level where it's compatible with the devices. So if I got them turned around there, I didn't intend to.
But if you have
Yes, sir.
20 times more turns on a secondary, that would be setting the step up to more.
Well, yeah, it was intended to be stepped down. So if I made an error in it, let's credit it to the fact that the hour is wrong and a number of other things. But we'll try to get through this.
One more question.
Yes. Okay, we're getting to the point where we're going to have to wrap this up. Depending on how serious you are about it and what you need to know about it, you can locate me, and I'm easily to be found, and I'll be more than happy to sit down and work with you on it, or tell you what I think about it, or what to do next, and that sort of thing. Yes, ma'am.
Mr. Smith, one of the things that really interested me is because I like working with youth, and you were saying that you work with Cub Scouts on these issues and show them how this works.
I give them the pieces, and they sit down and do their soldering and everything else and put them together, and when they hook it onto the battery, they're working.
Do you happen to have like a step-by-step video that you've made while you, so that we could bring it and show it to kids that we know?
Well, I tell you what, I'll get a group of Cub Scouts and we'll make you a video.
Okay, sir, that's a deal.
Sounds like fun. Thank you very much, Don.
Thank you.
And have a good night. We really appreciate you filling in the crisis here.
Thank you.